Hello, I am not an expert, and many people still do not believe that the solution to the Monty Hall problem is the correct solution. So today I'm going to go through a Java implementation of a Monty Hall game simulator. And we're going to run through the code. You don't have to know Java to get this video. I just thought it would help to explain it to make sure that you in fact trust the way this simulator was built. So this is just a simple JavaFX program. Perhaps I'll do some videos later on how to get started with JavaFX. And it's just going to play a bunch of games of the Monty Hall problem games, I guess. And we're going to do both strategy of never switching your door and the strategy of always switching your door. And we're going to show our winning percentage in both cases, and we're going to play the same number of trials in both. So that's what our UI is going to look like. Now to get started, I made a reward class. It's a very simple class. As you can see, there's literally nothing in it. I use it so that I can make a treasure class that extends rewards. So treasure is a reward, and a goat is also a reward. And that's all there is to the reward and treasure and goat class. Let's look at what a game looks like. So here's the constructor of a game. So whenever you make a game, we have a strategy of keep or switch right there. That's how we define those two things. And we're going to give ourselves 3 doors. So we're going to make an array called doors that's going to be of type reward. So when you build a game, the first thing we do is we make a doors an array of 3. We have 3 doors. And here is our pool that we're going to draw from to put the treasure and goats behind the doors. So our pool is going to consist of 2 goats. As you can see, we add 2 goats here and 1 treasure. Now we're going to randomly choose something from our pool and put it behind each door. So we're going to do this line 3 times, and each time we pull something out of our pool randomly. So here's our math.random call, depending, and we multiply by the size of our pool each time, which shrinks because we're calling .remove. So this just guarantees that we do a little bit of randomness in placing 2 goats and our treasure behind our 3 doors. And that's all there is to the constructor. All it does is place the 2 goats and the treasure. Now, when you call play on a game, we return a Boolean value of true or false. True if you win the game, and false if you lose. So you have to pass in what strategy you would like to use to play. So if your strategy is to keep whatever door you initially chose, all we have to do is randomly select one of our doors, and then we check if it's an instance of treasure or not. And that's it. That's all we have to do. We randomly choose a door, and if it's an instance of treasure, we won. Otherwise, this returns false. Now, it's a little more interesting if our strategy is to always switch doors. This is probably not the best way to implement this, but I thought it was perhaps the clearest representation of the linear events that happen through the Monty Hall game. So the first thing we do is we pick a door, just like we did in this case, but we're not going to check if it's instance of treasure or not because we don't know at this point. And we randomly select an index for our door. So we have 3 doors, and we randomly choose one of them, and we keep record of it here. So far, we haven't done anything really different. Now, Monty Hall is going to reveal a goat to us, right? So one of the doors we haven't chosen is going to reveal a goat. So all this part does is it creates a list of indexes where the goats live. So we have to do that in code. Now, at most, there's 2 goats, right? If we chose the treasure, there's still 2 goats behind, well, I guess there's a goat behind each door that's left. So all we do is we go through each door, and if it's the one we chose already, we skip it. So continue pops us out of this for loop, and then we go on to the next instance of the for loop. So this for loop happens 3 times. All right, if we're not currently dealing with the door that we initially chose, We check if it's an instance of goat, and if it is, we add it to our indexes of goats. That's all there is to that. And now here's the point where Monty Hall actually reveals a door to us. Okay, we're going to represent that by storing it here in this variable. Which one did he reveal to us? Well, we randomly choose one from our goat indexes. Now usually, well, not usually, but sometimes this is going to only have one element, sometimes it's only going to have two. And we randomly choose one to reveal to our player here. Now, my strategy, remember, is to always switch. So now, what door is left? I've got the door that I chose initially. He has revealed to me a door that has a goat behind it. There's only one door left. Which one is it? So this little for loop goes through each door. And if it's the one I already chose, if not equals, if it's not the one I already chose, and it's not the one that was revealed to me, that's the door I'm going to choose. And we go ahead and break out of this for loop early, just to save a little computation time. If, for instance, the very first door is the one that we didn't choose initially and wasn't revealed to us, then we can just break out of this for loop, and we don't have to do it 2 more times. So now that we have our new choice, we check if that is an instance of treasure or not. So all this hubble-be-doo is just to switch doors, and here we finally just check if it's an instance of treasure again. And if somehow you give us something that's not the only 2 strategy things, which is impossible because there's nothing else there, then we throw an error, which never happens. So let's see what happens when we play this simulator. I guess I should show you what happens when I click the Run Simulation button. That would be helpful. Let's do that. So here in our FXML controller, I've made the font rather large here. So whenever you click this button here, we're going to run, currently I have it programmed to run 100,000 games. So it's going to play the Monty Hall problem 100,000 times with both strategies. So essentially it's playing the game 200,000 times. So create a game here. It's the first thing we do. Well, besides increment the number of trials we've done so far. And remember, creating a new game, all that does is it puts goats and treasure behind the door. That's all that does. And now we play the game with switch strategy. And this is checking if this returns true. That's checking if it wins. So if playing the game with a switch strategy returns true, then we increment our win count for always switch. And then we play a game using our keep strategy. And we check if we win, because this returns true or false. And if it's true, then we increment our never switch strategy, our keep the initial door strategy. We increment the number of wins there. And then in each instance, we output how we're doing. So we set the text to this to be the percent that we win. We multiply by 100, and we tag on a percent here so that it looks nice. And we do the same thing for our never switch case. And of course, we set the number of trials, and it's equal. We play the exact same number of switch strategy games as keep strategy games. So now, let's see how we do. So playing the game 100,000 times, never switching doors, it's exactly what we would expect. Hopefully what you would expect. 33% of the time, we win, approximately. And if you use the always switch strategy, approximately 66% of the time, you win. Now, if I click this button enough times, so now we've done 200,000 trials. If I click this enough times, the law of large numbers is going to start kicking in, and this is going to get closer and closer to 33.33333, because that's the mathematical truth of how often we would win. And this is going to get closer and closer to 66.6666666666666. But I won't sit here and click that long. There's over a million trials. You can see that it's a much better choice to always switch doors. So there you go. There's some empirical evidence for the solution to the Monty Hall problem. If there's anything you would like me to do a video on, by all means leave a comment below, and if I find it interesting and if I have time, I'll make a video explaining it. I am not an expert, and thank you for watching.